and he will give a talk on the Helgason conjecture.
Well, thank you very much for the invitation to speak here. I will give a talk on this paper. I hope everybody can see this. This is from a while ago. We published this in 2022. This is actually a paper on a proof of a new proof of a theorem by Schmidt and Kashiwara. This original proof by Schmidt and Kashiwara is something I certainly cannot read. This is in technicalities way above my level, and we try to give a more elementary proof. The problem with the theorem is that it's a very strong theorem, but it has not been applied very much. And I think the reason is that it's maybe not so clear what this theorem is good for. And one of the things the theorem is good for is for the Helgason conjecture. So I will begin by the Helgason conjecture, then at some point go over to this theorem of Kashiwara and Schmidt. And then, if time permits, I will say a few words about our new proof. Okay, so I will start with the Poisson transform, a very classical setup. So I take the disk, the unit disk, in the complex plane. So all elements Z of length at most, well, smaller than 1. And this has a boundary, which is just the circle, unit circle. And on this, you can then define a Poisson transform on this circle. So basically, let's say for a continuous function phi on S1, I define the Poisson transform of phi as a function on the disk. And I do this by setting the following. So I map an element Z to the integral over S1. And then I integrate this phi against the Poisson kernel, and this is given by the following formula. You don't necessarily see here a lot, it doesn't matter too much. And this measure du, this is the normalized rotation invariant measure on S1. The point of doing this is that this gives you basically a harmonic function with boundary value equal to phi. So there is actually an inversion formula, which is basically giving this boundary value. So if I take a radius, limit of a radius going up to 1 of the Poisson transform of phi, and I put here then polar coordinates, then I get this phi of I theta. So in that sense, this is a boundary value. This is the inverse of this Poisson transform. And now the theorem is the following. So the theorem is saying that this Poisson transform actually extends to a rather large space. This is the space of analytic functionals or hyperfunctions of functionals, linear functionals on the space of analytic functions on S1. The outcome is always an harmonic function, smooth functions on the disk. And the theorem is that this is an isomorphism. This is a very classical result, and basically what the Helgason conjecture is doing is generalizing this to a much larger context by basically interpreting the ingredients that we have here. So we have here a disk. This will be a Riemannian symmetric space. We have the boundary of the disk. This will be the boundary, a part of the boundary of the Riemannian symmetric space. And we have here a Laplacian. This is an invariant differential operator. So we will look at the algebra of invariant differential operators. Okay, so basically we want to think of the disk as the hyperbolic space, or the Poincare disk. So just to see how this interpretation should work, I will have a look at the group SL2R. So this is the group of 2x2 matrices with determinant equal to 1. This group acts transitively on the upper half plane. So I will do this via the upper half plane because there the action is nice. So the action works as follows. So if I have a matrix with A, B, C, D as matrix coefficients, and is acts on Z by AZ plus B divided by CZ plus D. So the usual Möbius transformations. There is a map from the upper half plane to the disk, which is an obvious map. So I take Z minus I divided by Z plus I. This is a diffeomorphism. And by conjugating this action by this diffeomorphism, I get an action of G, a transitive action on the disk. And this formula for this action is not so nice, so this is why people typically don't write this. This is the way to think about it. Transitively on the disk. Okay. The stabilizer of the origin, 0 and E, is SO2. This is a maximal compact subgroup of G. And this makes actually that the disk, so because we have a transitive action, that makes that the disk is actually isomorphic to the Riemannian symmetric space G mod K. This G action extends continuously to the closure of the disk. So S1, which is the boundary of the disk. This is now also one G orbit. And it's actually a G mod P, where P is a minimal parabolic subgroup. So this is the standard minimal parabolic, let's say. So we have the matrix, the group of upper triangular matrices. So AB, 0, A inverse, with AB in R and A non-zero. Okay, so this basically prescribes us how to generalize this setup. So from now on, G will be a real algebraic reductive group. K is a maximal compact subgroup. P is a minimal parabolic subgroup. And M is the intersection of K and P. Now, for those who are not so familiar with these notions, it's perfectly fine to think here about SL2, SO2, the upper triangular matrices, and then M is plus and minus the identity. I think that's already an interesting kind of case. Okay, so here the point is with these choices is that we have a decomposition of G into a product of K and P, but then there is an overlap, and this is this M. So actually G is isomorphic to K times, or diffeomorphic to K times P, where you have to mod out the M action on the right from on K and from the left on P. Okay, so I will have to talk about representations. So let me first say what the representation of G for me is. This is going to be important for today's talk. So a representation is a locally convex Hausdorff topological vector space equipped with a group homomorphism and this group homomorphism is from G. So let's call this topological vector space V. The group homomorphism goes from V to the the group of invertible linear maps on V. Let's call this map rho, such that the induced map, so which maps a pair G and V to rho of G times V, so that this is continuous. So important here is for today that I don't assume my topological vector space to be Banach or Hilbert or anything like that. I want to allow a lot of things. Okay, so the representations I want to look at are called the spherical principal series representations. And these are the representations that are of fundamental importance for harmonic analysis on G mod K, on the Riemannian symmetric spaces. So I will give a description of this. I try to avoid as much notation as possible, so this will make that maybe some of the notation is slightly different to the experts than what you're used to, but you will recognize, I think, what I'm trying to do here. Okay, so the first thing that I need is the modular character. This is a character on P, so it's a group homomorphism from P to the positive numbers. And this thing can be computed as follows. So an element from a group acts by conjugation on its Lie algebra. That's what this add of P is doing. So it acts by conjugation. So this is now a linear map. So I can take the determinant and I take off that absolute value. So this is a multiplicative kind of a map. So this is a character. There's a character of P. What's important is that the restriction to M is trivial. And this is because M is a compact group, and there are not so many characters from a compact group into the positive numbers. Okay, so now I fix another character. I call this big lambda, because typically the notation is with small lambda, but it's a slightly different object. So this is to remind everybody what this is about. So from P to C cross, this could be just a complex character. But I want, and this is necessary to get the spherical principal series, I want that the restriction to M is again trivial. Okay. Now, the spherical principal series representations, they are built on a space of sections of a line bundle, and this line bundle is basically the following. So I can make out of these two characters the a representation, a one-dimensional representation of P, and I take for that the square root of delta, which is again a character. I multiply it by lambda, so this is now a P representation, and then I multiply that by G from the left and mod out this P. This is now a line bundle over G mod P. So this is basically what you should do, and then this comes with the natural G action. This delta is here because G mod P does not have an invariant measure, but you can still integrate densities, and this is delta, this modular character is basically the character that's associated to density. So this is why this thing is there. Now, what many people do, and I will do that today as well, is make the mistake to go to the compact picture. The compact picture is making the space, the representation space nicer, but it's making the G action much more complicated, so as we will see. But that's basically what you have to pay for getting nice representation space. Okay, so in the compact picture, the representation space will look as follows. So it is a space of functions, distributions, whatever, on K mod M, where F is, well, C infinity, or it's CK, or it's analytic functions, or it's distributions, or it's hyperfunctions, or it's LP space. I don't particularly care. So I want to have basically all possibilities. So this is basically important for what will come later. So the reason why this is somehow a good model is because G, as I said already, is decomposes in K times P, where you have to mod out this M, and this makes that G mod P, so the base manifold, is isomorphic, diffeomorphic to K mod M. So basically, instead of G mod P, we can look at K mod M, and then everything somehow trivializes, at least for this space on which the group should act. The G action is now given as follows. This is now more complicated than the natural action on G mod P. So I have to choose two maps. I will choose a map kappa from G to K and a map pi from G to P. And I want it to satisfy basically that it should be sort of a decomposition of an element in G to a K part and a P part. So it should be kappa of G times pi of G. And this should hold for all G and G. So the problem here is that k times p has this overlap in there, so this m. So this is basically causing that this is not uniquely determined, but the non-uniqueness is not going to cause any problems for us. Okay, so now for G and G, and for let's say an object from V, so something that lives on K mod M, and an element K, we're going to then define the group action as follows. I will define this, well, set this like a row. So this is basically the representation. The character lambda I will take in the notation because it's important. You can't now see anymore in the representation space with which character we're working. So I will put this in the notation for the group action here. This should then act on phi. This is going to be then again an object on K mod M. So I should be able to evaluate it on K mod M, let's say. And what this is now going to be is the following. So I take the K part of G inverse K. This should now be a coset on K mod M. So I'll write it like this. This I multiply by 1 over the square root of delta of the P part of G inverse K. And the inverse of lambda, again, of the P part of G inverse K. That is G inverse K. So that is the group action. Okay, so this setup comes with a natural pairing. This is one of the great benefits, again, of working with the compact picture. The pairing here is easy. You don't have to work with densities. You can actually work with a measure. So if I have two, let's say, continuous functions on K mod M, then I can just integrate them against each other. So I will call this the pairing of phi and psi. This is the bilinear version. So the integral over K mod M of phi of Km times psi of Km. Ekm. Okay, so the question is basically when is this pairing good, and this has to do with the G action. So we want this pairing to be G-invariant, and this is again why this delta is in the setup. So this pairing here is G-invariant, or well, for the G action given by lambda inverse, the character lambda inverse on the first component, so the phi, and rho lambda, so the character lambda on the second one. And so now you have this kind of nice anti-symmetry. If you don't put in the delta, then you have to put in a shift here, which is more ugly. So this is the pairing. What is also important is that there is a K-invariant factor here in these representations. And this has to, well, this is basically where this word spherical comes from. So we want to have spherical principal series. This means K spherical. So this means there's a non-zero K invariant factor. And this is the constant function on K modulo M. And I will want to look at this thing actually as an analytic function on K mod M. So this thing is K invariant. With respect to rho lambda, but actually I want to do it with lambda inverse. It doesn't matter which character you take here, it's always K invariant, but for us it's important to do this with lambda inverse. Okay, so with this data, I can now set up the Poisson transform. And this you can do in a very large kind of setting. So I take here a hyperfunction on K mod M. And then I can already define the Poisson transform. This depends on this character lambda, so I put it in the notation. This is now going to be a function on the Riemannian symmetric space G mod K, values in C. And what this thing is doing is the following. So if I evaluate it on a coset GK, then, so what can I do? Well, I take this K fixed vector. I act on it by G. So G is not uniquely determined by the coset, but the only sort of non-uniqueness is the right multiplication given by right multiplication by elements from K, and which is fine because this vector is K invariant. And I pair this thing now with this hyperfunction phi. So this G action on this analytic function is going to just produce again an analytic function, and I can pair it then with a hyperfunction. So this is what the Poisson transform is, and if you would take lambda equal to 1 over the square root of delta, and you just work out these integrals and what this all means, then you will get, for SL2R at least, you will get the Poisson transform back that I talked about on the first slide. Okay, so this should be good for something. So as I said already, we want to now look at the invariant differential operator. So I will denote this by d of gk. So this is the algebra of invariant differential operators on G mod k. And now the point is that these images of the Poisson transform are all eigenfunctions, joint eigenfunctions for this entire algebra. So this can be phrased as follows. So there exists a character chi lambda that is completely determined by lambda from this algebra of differential operators to C, such that if I apply an invariant differential operator to the Poisson transform of a hyperfunction phi, then this is just the character evaluated at this differential operator, so a scalar, times this Poisson transform of phi. And this is true for all d in the differential operators, invariant differential operators, and phi in the hyperfunctions on K mod M. Okay, so this automatically maps to joint eigenfunctions. And what is here important is that actually these the images of this Poisson transform are always smooth, and this has to do with the fact that there is an elliptic, well, at least one elliptic invariant differential operator in d of G mod k. So by elliptic regularity, you get that everything here is smooth. So elliptic regularity implies phi lambda phi is a smooth function on G mod k. Okay, so let me give the space of eigenfunctions for this character determined by lambda a name. So I will write E lambda G mod k for it. So these are all smooth functions on G mod k. With the property that for every d in the differential operators, invariant differential operators on G mod k, I have that d of phi is given by chi lambda of d acting on f. So d of f is chi lambda of d acting on f. Maybe what's also good to say here is that every nice character of this algebra of invariant differential operators on G mod k is given by such a chi lambda. So you can always find a lambda so that you get the character you want. Okay, so with these data, I can now write down the Helgason conjecture. This is no longer a conjecture, but still called a conjecture. There's one assumption one has to make. So the constant function on K mod M should be cyclic for the representation for lambda inverse. Also, so this means that that this factor here is not contained in a proper subrepresentation. Subrep. Okay, so that is the one assumption. Under this assumption, we get now the following statement. The Poisson transform, as defined on the hyperfunctions on K mod M. As I said already, this maps to these smooth eigenfunctions on G mod K. And this is an isomorphism. So we get all of these eigenfunctions in this way. The assumption is there to guarantee injectivity. So actually that is equivalent to injectivity. This is easy to see. This is not the deep part of the theorem. The deep part of the theorem is assuming this constant function is indeed cyclic, that then this Poisson transform is actually surjective. That is the deep part. There's a proof, 1978 in Annals by 6 Japanese mathematicians, Kashiwara, Kawata, Minamura, Okamoto, Oshima, and Tanaka. A fantastic paper, but not so easy to read. And this is because of the obvious fact that we're dealing here with hyperfunctions, and a lot of people, me included, are not so used to doing that. So this is not all that easy. There have been attempts to make it easier. Let me mention one of these attempts. So this is by Aprameyan, Parthasarathi, and Hilbert and Hansen. I actually don't know what happened to this article. It's still in the archive, but I couldn't find a published version of it. Maybe this has to do with the fact that it's not quite complete yet, as far as I understand. So this is for generic characters lambda, and somehow the others, sort of not all characters lambda for which it should hold are included here. Okay. So that is the Helgason conjecture. Let me now go to Schmidt's interpretation of this conjecture. Schmidt's interpretation. Let me also show you the article in which he does this. This is from 1985, a very short paper. This paper contains an idea and a claim, and the claim is not proven. This is done later by Kashiwara and Schmidt. But the theorem that is claimed already in this paper, it's not so easy to prove, it seems. And the proof that Kashiwara and Schmidt give, is very technical. Uses a lot of heavy machinery, and I'm utterly unable to read any of this. And as I said already in the beginning, so our attempt was to somehow give an alternative version of this paper. But what this paper by Wilfried Schmidt indeed actually does is that it tells you how to think about the Helgason conjecture from maybe an even more representation theoretic point of view. Okay, so I need to introduce a number of things for this. In particular, I need to introduce Harish-Chandra modules. So if I have a representation phi of G, which is sort of nice, as in not too big maybe. So I want to have that. I wanted that it has finite k multiplicity. So this means that if I restrict it to k, then it decomposes into irreducible k representations. And I don't want that any of these k representations occurs infinitely often. So everything should occur finitely often. So this is, for example, the case for the spherical principal series. I can define here a subspace vk finite of k finite vectors. So a vector v is called k finite if the dimension of the span of the k orbit, so let's k act on all of on v, so I get this orbit, I take the span of this, if this is finite dimensional, so the dimension is finite. The problem with this space is that it does no longer carry a G action. So if I take a k finite vector, I let a typical element from G act on it, then there's no reason to assume that the result is going to be again k finite. But the good news is that you still have an infinitesimal action. So the Lie algebra of G still acts on it, and also k. I mean, there's no problem with the k action. So it's a G and a k representation, if you want. Okay, so if I have V as before, so some space of objects on k mod n, and rho lambda as before, where f is whatever you wish, c infinity, ck, etc. Then you always get, regardless of what you have here for f, regardless what you have there, you always get the same space of k finite factors. And this is often denoted as follows. So it's sort of regular functions on k mod m. So you can think of this as the space of finite Fourier series. Finite Fourier series. So if you think back to G is SL2R, then K is SO2. K mod M is actually a circle. So you can take such a function or a distribution or hyperfunction on K mod M on the circle, and then decompose it as a Fourier series. The ones that are K finite are precisely those for which this sum is finite. So finite sum of objects. So these are the nicest kind of vectors that exist. The constant function on K mod M is one of these. The problem is just that this space is not a G representation anymore. Okay, so one of those things I call now a Harish-Chandra module. So this is a GK module. So it carries this action of the Lie algebra G and the action of the group K. With some compatibility, which you automatically get if you take this K finite vectors over representation. This should be finitely generated, whatever that may mean. And it should have finite K multiplicities. So the K finite vectors in a spherical principal series would be a Harish-Chandra module. Okay, so now we know how to go from representations to Harish-Chandra modules, but actually we want to also go back. And this is called a globalization. So globalization of a Harish-Chandra module. Let's call it curly V. This is a G representation. So anything on some locally convex host of vector space. Let's call it V rho. Such that the K finite vectors in V are isomorphic as a GK module to the given Harish-Chandra module. And basically what this discussion of before shows is that for the also for the spherical principal series, you have many globalizations for every given Harish-Chandra module. So these things are very far from being unique. So are not at all unique. Okay. But there is some order in the chaos here. This is what Schmidt describes in this paper I showed you. This is actually with complete proofs. So for a given Harish-Chandra module, let's call it curly V again, there exist globalizations, which I will denote by V min and V max, which act as the smallest and the largest possible globalization, so the minimal and maximal globalization. So let me try to say what that means. So that for any other globalization, let's call it V, we have that V min embeds into V, and this embeds into V max. So V min and V max are up to isomorphism unique. This is easy to see from this description. And here you see that V min is the smallest one and V max is the largest one. You can actually write down formulas for this. So you can basically identify what these things are. So V min, let me just do this, and then V max is somehow obtained from V min. So V min is obtained by taking convolutions of a test function phi and a vector V. This convolution should be understood as follows. I take the integral over the whole group G of the test function times x acting on V, and then I integrate over x. Where V is any element from the Harish-Chandra module, so K finite element, and phi is a test function on G. Now this you can do in any globalization, this kind of procedure, and it will give you a subspace that is G-invariant and closed. So in that sense, you always get in any globalization, you get this subspace or the subrepresentation for this subglobalization V min, if you like. So we can always build this. This comes with a topology. So this is the topology induced from the topology on from topology on the test functions. Okay, so Vmax is obtained by dualizing this kind of construction. So they're in some sense dual to each other. And what's very important here is that this construction is functorial. So the map from the Harish-Chandra module that assigns to the Harish-Chandra module the minimal globalization or the maximal globalization, these two maps are functorial. And this is a very strong statement. So basically what this says is that if I have two Harish-Chandra modules and I have a GK homomorphism in between, so a homomorphism of Harish-Chandra modules, which is just an algebraic property, then that homomorphism will lift to a continuous G-equivariant map between the minimal or the maximal globalizations. So there's also this kind of algebraic information there. It's a G-equivariant map. But more importantly, there's analytic information there. It's continuous. You get the continuity for free.
Can you repeat this thing? What did you say? This functorial thing?
Yeah.
What did you say once again? Can you repeat that?
So if I would have, let's say, some map, some homomorphism between two Harish-Chandra modules. So this is, let's say, a homomorphism of Harish-Chandra modules. Then it lifts. So I get here the map to Vmin. Let's just let me do the Vmin for now. Let me do the Vmax version because this is how it will come back later. And also here. So let me call this Wmax. So what I get here is a map. So if this is a homomorphism of Harish-Chandra modules, then this I get here a map between these maximal globalizations, which is continuous and G-equivariant. And the continuity is for free. I mean, that this G-equivariant is not so much of a surprise. This is just because you have this GK equivariance upstairs. But the continuity, this is the point. You get this for free. Okay, so with that, we can actually attack the Helgason conjecture after we have identified basically what Vmin and Vmax are. This is the claim that Schmidt makes in his article. I will write it as the theorem of Kashiwara and Schmidt. Okay, so for any Harish-Chandra module, let's say curly V, we have that Vmin is what I will denote by V omega. This is the space of analytic vectors. And Vmax is also identified, this is by dualizing, as the space of hyperfunction vectors. Okay, so let me say what this means for our spherical principal series. There we have that Vmin is just the space of analytic functions on K mod M. And Vmax is the space of hyperfunction vectors on K mod M. Hyperfunctions on K mod M. Okay, so this is actually a deep theorem. Not so easy to see. So here you really have to do something. And as I said, this proof of Kashiwara and Schmidt is not something that I think most people are comfortable with. So probably our proof is likewise not something that most people would be comfortable with, but I hope that it at least improved things a bit. Okay, so let me explain how to relate this to the Helgason conjecture. This is again from the paper of Schmidt, what I will say here. So actually Helgason in 1976 already proved a nice statement. So he restricted the Poisson transform to the K finite vectors. So in this case, this would just be this notation again, the regular function K mod M. And what then comes out, and this is what he proved, that this is isomorphic to the space of k finite vectors in the space of joint eigenfunctions on G mod k. So he proved that this is an isomorphism. This doesn't require any analysis. This is an algebraic statement. This is not so difficult to do. I mean, once you know that this ought to be true, then you just write it down by manipulating the definitions here. Okay, so what we now can do is take maximal globalizations. And what I now get is, okay, so the maximal globalization of this first one, and I get the maximal globalization of the second one. And functoriality gives me now an isomorphism between these maximal globalizations. Okay, so this theorem of Kashiwara and Schmidt, this is K and S, says that this maximal globalization is given by the hyperfunctions on K mod M. And on this side, I can use elliptic regularity and see that whatever this maximal globalization ought to be, it still actually lands in the smooth functions, which are eigen. So it's actually all of E lambda of G mod K. Okay, and now we have the Helgason conjecture, proof of the Helgason conjecture, basically for free. But of course, you have to pay by actually proving the theorem of Kashiwara and Schmidt. So this is actually a very powerful tool once you have this, but it hasn't been applied very much, and I'm not entirely sure why, but maybe because it's just from the statement itself not so clear what it's good for. Okay, so what we did is that we provided a new proof for the fact that phi min is isomorphic to the analytic functions, and with that you get then the statement also for the maximal globalization. Okay, so in the remaining time, I will try to give an idea of what we're doing. So we have these two spaces, and both actually admit nice filtrations. So I will first describe this for phi min, and then I will do it for the analytic vectors. Okay, so just to recall, phi min is given by convolutions of test functions on G with k finite functions, so these k finite vectors, so these elements from the Harish-Chandra module. Okay, so basically what we now want to do is take the usual filtration of the test functions by size of support, and then make a filtration out of that for phi min. So for large R larger than 0, I define CR of G as the space of all test functions with the property that the support of F is contained in a ball of radius R. Okay, so what is the ball? You can take this by K fixed, and then basically you can maybe use the Riemannian metric on G mod K to define a ball or so. So this, whatever you do here, it doesn't really matter so much. It will always give you a filtration anyway. But whatever you would think of as a ball, you should take here as a ball with a certain radius. Okay, so then I can define then also the corresponding subspace of phi min by just taking convolutions with these test functions with this restricted support. Okay, so then I get the direct limit. So phi min is the limit for R to infinity of phi min R. Okay, so this is the filtration for phi min, just by taking the usual filtration on the test functions. Now we want to give also filtration on the analytic vectors. That we do as follows. So you can actually complexification this group K. This is because it's an algebraic group, so you can just take complex points. So this is then a complex group of the same, so the complex dimension is the same as the the real dimension of K. K sits in here. There's some nice structure here that you can think about. Okay, so for small r positive, I define then a kind of a complex neighborhood of the real group K, denoted by KCR, as follows. I take this group K and multiply it by the exponential map applied to the set IX, where X is an element from the Lie algebra of K, and the length of X I restrict by R, by small r. So the smaller small r gets, the smaller this neighborhood actually is. And then I define a subspace of the space of analytic vectors by taking all analytic vectors with the property that the map from K to KV, so the orbit map, extends holomorphically to KCR. So the fact that we have here an analytic vector will actually imply that it extends to some neighborhood of the real group K. The question is, how far does such a vector extend? So I take here everything that extends at least to this neighborhood KCR. Now this can also be topologized. This is with the topology of uniform convergence on compacta. Whereas the previous filtration is just somehow using the topology of the test functions. Okay, so now again we get that phi omega, so the analytic space of analytic vectors is given by a direct limit. Now for r to 0 of phi omega r. Did it with a sub, let's keep it like that. So. Okay, so we have these two filtrations, and our idea is basically to show that these members of these filtrations actually sit in each other. So we have some kind of a sandwiching. And this is the theorem that we proved. Gimperlein, Krötz, myself, and Henrik Schlichtkrull. So we have two inclusions. One we call the analytic inclusion. This looks as follows. For all small r positive, there exists a big R positive, so that VR omega, so the filtration, member from the filtration for the analytic vectors, sits in the space phi min r. And we can give some kind of bounds on this big R. So R needs to be bigger than a certain threshold, R0. So maybe I should write this as take this. And we have another formula here. So log R divided by R squared is smaller than constant times small r for certain C and R not larger than 0. As I will explain later, this kind of bound that we have here seems, at least to me, seems not to be the correct one. As in, it works, but it's not sharp in any way, shape, or form. The next one is better. This we call the geometric inclusion. And that's just basically the other way around. So for all large R, there exists a small r, such that VR min embeds into VR omega. And here also we can write down some kind of formula. So take here a small r smaller than C times e to the minus C big R for certain constant C and C larger than 0. So this geometric inclusion, at least the bound here, I think is a lot better. And this has, yeah, so we computed some examples. So at least it seems that the shape of this bound, as in it needs to be this kind of exponential decay, seems to be the correct thing. As a corollary of these two inclusions, we get now that V min and V omega are the same. So the point here is, however, that we get a kind of, so a quantitative version of this equality, right? So we can actually say which elements from this filtration sit in what other elements from the other filtration. So in that sense, this is close to a kind of a Pélé-Wiener theorem. So it's a Pélé-Wiener type theorem. So what is a Pélé-Wiener theorem? Well, you want to take basically the space of test functions and then apply a Fourier transform and then describe basically describe basically the image of the space of test functions with a given support, like CR infinity of G. So you can do this for the group. There are also Pélé-Wiener type theorems, Pélé-Wiener theorems. They use all representations, and basically what we are doing here is that we take the Fourier transform attached to one representation and then somehow try to characterize nevertheless the support of such a test function. So this is a way to think about it. This is why we call it Pélé-Wiener type theorem. Actually, for a Pélé-Wiener type theorem, you would want to have really sharp estimates, right? So sharp control over what these bounds are, and that we don't really have. So there's a lot of room for improvement there, I would say. Okay, so let me try to give at least a kind of a hint where these inclusions come from. So as with all proofs that are complicated, I suppose the first thing you do is try to simplify things. And this we do by reducing to the spherical principal series. The reason why I assumed that the group G is algebraic has to do with the fact that we want to take a complexification of K, but you can do that anyway. So maybe that's not so necessary for that. There's other ways of doing that. But we also need to do this reduction to the spherical principal series. And for that, we actually need this algebraic nature of the group G. Okay, so the geometric inclusion, maybe I will talk about that first. So here the idea is the following. So I take a V from my Harish-Chandra module. Then I can look at the orbit map, but on the whole group G. So I map an element G to G acting on V. What is known, this is something that Bernhard Krötz has been working on for a long time with several people, is that this extends to the crown domain. So there is a geometric object. So the map extends holomorphically to the crown domain. There's a geometric object called the crown domain. It's some kind of complex neighborhood of the group G. This crown domain is often called Xi. Doesn't really matter what it is here. I just want to explain the idea that we have here and why we call this the geometric inclusion. So the idea is now the following. So we are not really looking at k-finite functions because we take this convolution with a test function. We have the support contained in a ball of radius r. So given such an r, we want to basically find small r, so that basically now the following holds. So I know that I have a holomorphic extension to Xi. I have a bit of fuss coming from this ball. So I need basically this ball times sort of the wiggling room I want to have in K, still sitting inside this Xi. So this is basically, if you wind down the definitions, this is basically the inclusion you would want to have, and you want to find the largest small r so that this is still true. And we compute this in some examples. As I said, so the kind of estimates we get there for the geometric inclusion don't seem ridiculous. So they're probably quite okay. Okay, so for the analytic inclusion, we have to work a lot harder. This is actually where most of the paper is devoted to. So we take now an analytic vector which extends to KCR, small r. What we now want to do is construct a Pele-Wiener function. This Pele-Wiener function I will call FV. Now I will write some letters for those who know what these letters mean. Good. Otherwise, just don't worry about it too much. PW, this is the Pele-Wiener space. I have here AC star. This is the space of characters, if you wish. So my lambda is coming from this space here. This is some kind of vector space. Doesn't matter what it really is. This Pele-Wiener function should have values in C infinity of K mod M. And it needs to encode a certain kind of support. So let's say I want to take the Fourier transform of a test function with a support in a ball given by radius r. So this is what this r comes from. So this basically the nature of this Pele-Wiener space is very similar to what you have for the Euclidean Fourier transform, except for maybe that the target space here is a space of functions on K mod M. Okay, and we do this for some r larger than 0. And this is basically where this estimate for r comes from. We want that this Pele-Wiener function satisfies something nice, so I can evaluate it in the character that I'm interested in, the character of my principal series. And then I want to get my original function v back. So this is how f of v and v are related. And this is not easy. So it's in general not easy to write down any Pele-Wiener function. This is really a struggle, and we somehow have to do something here. And I think in the course of doing that, the estimates that we get, so we build something and then we have to estimate it, see that it is of Pele-Wiener type. And even for what we built, I think the estimate is not optimal. So probably this formula that I showed before here, this log r over r squared smaller than c times small r, I think this is not sharp in any way, shape or form. And not even for the thing we built. Okay, so this Pele-Wiener space is actually the image of a space of test functions. And this is by the Helgason Pele-Wiener theorem. This is one of the celebrated theorems of Helgason. The Pele-Wiener theorem on G mod K is this. So to obtain. Okay, so a Pele-Wiener function is automatically the Fourier transform of some test functions on G mod K. And this R basically tells you from what support this thing is supposed to have. So I want to maybe describe it as a function, a test function on G, and take it right K invariant so that it actually is a test function on G mod K if you wish. Okay, and as I said, this is then basically so that the standard Fourier transform for functions on G mod K gives you this f of v. Okay, so then we get the correct thing. So if you now just unwind definitions, v is f of v evaluated at lambda. This is how I've chosen f of v, how we built this thing. This is actually the Fourier transform of a compactly supported function phi evaluated at lambda. But this Fourier transform is nothing but a convolution. It's actually the convolution, and here you need to specify the group action. So this is with respect to rho lambda of the constant function on K mod M, which is a K-finite function. So it lives in the Arashandra module. And since the support of this phi is in the ball with radius r, we land in the minimal globalization. So this element from the filtration with the index r. So the hard work is really in the construction of this Pele-Wiener function. And I think, as I said, so there's a lot of room for improvement there. But basically what we show is well, I suppose, proof of concept. And with that, we actually give a new proof of this theorem of Schmidt and Kashiwara. With that, we hope that we actually demystified that theorem a little bit. Okay, let me end here.
Yeah, thank you very much for a very interesting talk.
Mm-hmm.
Let's see if there are some questions from the audience.
Given a GK module and you have infinite number of globalization, okay? Can you say that when this globalization be a unitary representation? Can you
Well, I mean, certainly if you want to have a unitary representation, then you need to make the globalization on the Hilbert space. Okay, so that is, so let's say, so globalization V. This thing here needs to be so unitary, will imply that V is Hilbert. Okay, but this is not enough. And now this becomes a very difficult problem. So this is something that, for example, David Vaughan has worked on for an extremely long time. So this is Atlas program. This is some piece of software which basically allows you to determine what is unitary and what is not. So it's not so easy to see from the Harishchandra module whether this thing is unitarizable or not. So that's the issue here, and that's so this is not so clear. For example, if you look at the spherical principal series, these things are unitary when lambda is, so if I take lambda, the character, actually mapping to S1 in C star, so this is a unitary character, or C cross. So if I take it like this, then this spherical principal series is unitary. But if I take any other character, some random character, so that there's also maybe some complementary series or whatever. But if I take some other character, yeah, who knows? Who knows? It's not so easy to see. I mean, so that this is then not unitary. And the reason is that this representation space is always the same. It's still a Hilbert space. You can just do it on L2 of K mod M. But now the group action is different, right? So that's the issue here.
Are there any other questions from the audiences?
Yeah, maybe I just wanted to say that paper remains as it is. I think 2 years ago or something like that, Joachim wrote saying, okay, should we maybe finish so that it is in this the Kobayashi volume. But at that time I didn't have time, so it was, yeah, it is as such. Some parameters we couldn't handle, we didn't try later, so it remains there on archive. So. Okay.
Yeah, but for generic parameters, I think it is a nice text. Yeah, so
yes,
it's quite clear. Yeah,
it is very, it's reasonably well written. Yeah.
Are there any more questions? Yeah, maybe not. If in that case, let's thank the speaker once again. Thank you very much.
Oh, thank you.